Okay, average rate of change. Okay, the average rate of change of y with respect to x is delta y over delta x. Delta just means change. It's a way of, it's a Greek letter. This is delta. Okay, this is, don't get scared. It's the only Greek letter that I'm going to introduce to you in this course. Okay, so that's delta, maybe epsilon, I don't know, we'll see. But delta just means change. Okay, and it's the change in y over the change in x, which really, if you think about it, is slope. Okay, isn't that what slope is? The change in y over the change in x, right? What was the slope formula? y2 minus y1 over x2 minus x1. Okay. Okay, the other way that we could think about this is, okay, this is slope, right? Slope of a line, right? So that's the average rate of change is the slope of a line. So the average rate of change is are going to be lines, and they're going to be slopes of lines. Okay, and so this is the average rate of change. Okay, the average rate of change. How on average, how much am I changing, right? On average, over two x values, how much do the y's change? Okay, so that's slope. We could also think of this as f of x2 minus f of x1 all over x2 minus x1. Okay, so this is the slope of a secant line. Okay, this is called the slope of a secant line. Okay, we'll get to what that means in a little bit. Okay, I'll draw a picture of this. Okay, so say that we have a curve, any old curve here, and say that we have at x1, we have a value f of x1, and then here, let me make it actually, let me move that over. There we go. Move that point over to here. Over here, we have x2 value, and this is f of x2. So the rate of change is going to be the change in the y's. How down did I go over the change in the x's? How much did I go over? And that is just the slope of what we call a secant line. This is a secant line that attaches to a line to 2 points on the curve. Okay, this is called the secant line. And the average rate of change over that period is just going to be the slope of that secant line. Okay, so let's see how this works in real life. It's a lot easier to define the abstract in terms of the concrete. Okay, for f of x equals x squared plus 1, find the average rate of change as x changes from 1 to 3. Okay. So as x changes from 1 to 3, let's find the average rate of change. Okay. Let's see what's happening here. So let's find the f of x2 minus f of x1. This is delta y over delta x. That's the average rate of change all over x2 minus x1. Okay. So this is going to be plug in x2. Well, what's x2 in this case? Let's figure out what's x1. Well, x1 is 1 and x2 is 3, right? So this would have to be f of 3 minus f of 1 all over 3 minus 1. Which is equal to, we'll plug in 3. Let's figure out what's f of 3. F of 3 is going to be the function evaluated at 3. So this is going to be 3 squared plus 1, which is 10. Okay, that's 10. What's f of 1? It's 2, right? All over 3 minus 1. Well, what's 3 minus 1? That's 2. So this is going to be 8 over 2, which is 4, right? Okay, you can think of it as 4 or 4 over 1. Okay, so the average rate of change here means that for every 4 units I go up, I go 1 unit over. Okay, that's the average rate of change. Now, let's see what happens here. What does this function, f of x equals x squared plus 1, look like? Well, it looks like a parabola. Oops, not that, at 1. Okay, looks like a parabola. Okay, up 1. Okay, and so it's saying that, well, what's the rate of change here? Okay, if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's go way up. Okay, on average, how much is this changing? Well, we have this point over here, f of 3, right? We have this point over here, f of 1. Okay, so this is when x is 1. This is when x is 3. And then what do we have? We have this secant line, right? And it's saying that every time I go up 4, I go over 1. Up 4, over 1. The average rate of change is 4 over 1. So I go up 4 over 1, up 4 over 1. That's the slope. Okay, that's the slope of the secant line through those 2 points. Move this over. Okay, so this is the slope of the secant line, okay, through the points, okay, what do we have? 1, 2, and 3, 10, right? So through the points 1, 2, and 3, 10, because that's where those points are located. Okay, now where are we getting the word secant from? Well, if we take a circle and we cut across the circle, this is called the secant. Okay, secant. Okay, so it's just saying we cut across this curve. That's a secant line. Okay, so we say here that the average rate of change is 4. The average rate of change is 4. Okay. Okay, the average rate of change is also called the difference quotient. Okay, the average rate of change is also called the difference quotient, and it's written a little bit differently. okay, it can be written in two different forms. It can be written as f of x2 minus f of x1 all over x2 minus x1, or it could be written as f of x plus h minus f of x all over h. And the one that we're going to kind of focus on is this guy here. Now, how does this work? Let's look at our secant line again. Let's take our parabola here and we'll look at our secant line. Okay. And let's call this, instead of x1, let's just call that x. Okay. And instead of x2, let's call this x plus h, where this distance here is h. Okay. Okay, so we went from x all up to x plus h. So this is going to be x comma f of x, and this is going to be x plus h comma f of x plus h, right? Those 2 points. So how do we get this thing up here? Well, we take the second y value. Remember, this is y2, this is going to be x2, this is y1, and this is x1, right? And so we're going to take y2 minus y1 over x2 minus x1. And what is that going to be? Well, that's f of x plus h minus f of x. That's y2. Or y1 is f of x. I'll zoom in on this for a little bit. Not too far. Okay, all over what? Well, all over x2, but what's x2? It's x plus h minus x1. But what was x1? It was x. So these x's cancel out. Okay, I wish my x's would cancel out. Okay, that's mean and cruel. I'm sorry. I digress. Okay, so f of x plus h minus f of x all over h, okay, is the difference quotient that we're going to be using. Okay, we call this the difference quotient. Okay, so let's look at example 2 here. For f of x equals x squared, find the simplified form of the difference quotient difference quotient okay. So for x squared, right? So for x squared, so how do we do this? F of x equals x squared. Okay, so we're going to say, well, what's f of x plus h? Then wherever we see an x squared, we're going to have to replace that with x plus h squared. So this is going to be x plus h squared. Okay, that's what that is. So I'm going to plug that in. I'm going to go x plus h squared minus f of x all over h. Okay. So now I need to know, well, what's x plus h squared? What's x plus h times x plus h? Okay, that's going to be minus f of x all over h. Okay, so let's FOIL this out. This becomes x squared plus xh plus hx plus h squared minus f of x. But what was f of x? What was f of x? Isn't that just x squared? Isn't that just my parabola? Yeah, sure, that's x squared all over h. And lo and behold, what do we notice? The x squareds will cancel out. That's kind of nice. I could also factor out an h in the top. Let's factor out an h in the top. This is going to be x plus x plus h, all over h. Okay, and what cancels? Well, the h's cancel, and I'm left with 2x plus h, and that's the difference quotient. Okay. Okay, so let's keep that in mind here. Okay, what's the simplified version of the difference quotient when f of x is equal to x squared? Okay, that's this guy here. Okay, so I'm going to keep that in my back pocket. Okay, does that make sense? Maybe I'll write it to the side here. Okay, what is the difference quotient? What's the function? And what's the difference quotient? Okay. What's the function and what's the difference quotient? So when I had x squared, the difference quotient was 2x plus h. Okay. So just kind of, we're going to keep a running tally here of what we've done. Okay. Because it's going to come in handy in a second, trust me. Okay. We're not doing this for our health. Okay, maybe for our mental health, but we're not doing this just to do this. This has a point. This whole thing has a point. And again, we got to like build, we're building the mountain, right? We're building the sandcastle. Every bucket of sand that we pour on builds the sandcastle more and more. Is anybody going to the beach this weekend? I think that's a prime destination, right? I think so. Well, I don't think I'm going to go to the beach. I think I'm going to go to the mountains. I think that's supposed to be 100 degrees this weekend. Oh, that sucks. I guess maybe if I go to the mountains, it'll be nicer. So yeah, I just got to find someone who will go with me. That's on my agenda. So my dog will always go with me, but you know, with the whole COVID thing, nobody wants to get within, you know, 10 feet of anybody. Exactly. Yeah, maybe like Mammoth Lake or something. That would be fun. That would be cool. Just take my dog, Mammoth Lake. Forget about everybody else for a while. Maybe that's the ticket. Okay. I'll see you up there, Christian. Okay. We'll do some calculus in between, you know, our casting. I don't think there's going to be much snowboarding up there, so you could try maybe on the dirt, like ride down the hill on the dirt. Right. So there's some people that do volcano boarding. Have you seen this craziness? They go on the top of a volcano and they like ride all the way down on the rocks. I mean, these are literally rocks that they're riding down on. It's like adrenaline junkies. They go to Brazil and they ride down this active volcano. Exactly. Like, you know, I thought, you know, esports was going to be like, you know, that was it. You're like, oh, you know, it's the BMX biking and the stuff like that. And it's just, people find crazier ways to, and crazier things to do. Like, yeah, let's just ride down an active volcano, pretend that, and hope that it doesn't erupt while we're doing that. Yeah, the sand dunes, I've seen that. That's been around since the late 90s. Like, you know, go to the Sahara Desert and, you know, try to not, you know, die from overexposure while you're riding the sand dunes. So you can go to Glamis, maybe get your get your snowboard out and, you know, scratch it all up on the sand. There you go. Like, I bought this $300 Burton snowboard so that I can go destroy it on the sand dunes. Sure, makes sense to me. Anyway, again, I digress. And why do I digress? Because this stuff is so freaking boring. So boring. That's why I digress. I'm just going to blame the ADD. Okay. But you have to know this stuff. Okay. Otherwise, we can't do fun calculus business stuff. Okay. You're going to be in a business meeting and people are going to say, oh, yeah, the elasticity of demand of this curve. And you're going to be like, huh? What? I don't know what that means. And then you'll be like, well, didn't you take business calc? And they're like, no, I don't remember anything. You're like, well, dude, okay, no senior VP for you. That's it. Okay, let's get to the calculiciousness. I think I just created a new word. Calculiciousness. How are you feeling today? Calculicious. Yeah, I'm awfully calculicious today. Nice. It's the deliciousness of the calculus that I am internalizing into my day. Yeah, calculicious. Count calculicious. Yes. 1, 2. He counts too, right? He's counts, calculicious. I'll trade him in for Count Chocula any day. That's a count that I can get down with. Count Chocula. Okay, number 3. Okay, for f of x is equal to 1 over x, find the difference quotient. Okay, so let's find the difference quotient here. So what was that? F of x plus h minus f of x all over h. Okay, so this is going to be 1 over x plus h minus 1 over x all over h. So now what I have to do here is find the common denominator. Find the common denominator. Okay, well, that's going to be x times x plus h. So if I add an x on the bottom here, I've got to add it to the top. If I add an x plus h to the bottom, I've got to add that to the top. So this becomes x over x times x plus h minus x plus h all over x times x plus h all over h. Okay, so this looks hard, but it's going to clean up. Trust me. Okay, it will clean up nicely, just like me. I clean up nicely. Okay, so at negative x, so x minus h. Okay, all over. Okay, x times x plus h. Okay, all over h. Okay, and what I'm going to do now is I'm going to do something kind of sneaky. Okay, is I'm going to take this h on the bottom. I'm going to put it over 1, because what happens when I divide by a fraction? Divide by a fraction. What do I do? What's the rule when we divide by a fraction?
You multiply the reciprocal.
Yeah, multiply by the reciprocal. Dividing fractions can be fun when we flip and multiply the second one. That was told to me by a student when I taught 8th grade. She's like, don't you know the rhyme? I'm like, no. It's like, yeah, dividing fractions can be fun when you flip and multiply the second one. I'm like, where'd you learn that? And she's like, oh, from my mom. I'm like, oh. She's like, oh, my mom is an elementary school teacher. I'm like, oh, that makes sense. So I learned it vicariously through her mom, who was an elementary school teacher. So we want to flip the one on the bottom, right? We want to flip the one on the bottom. So multiply by the reciprocal. Okay. So this is going to equal negative h over x times x plus h times 1 over h. But lo and behold, what does this allow me to do? It allows me to get rid of the h's. That's kind of nice. So this is negative 1 over x times x plus h. And that is the difference quotient. So again, we're going to go back to our list. And I'm going to say that when I have 1 over x, what's the difference quotient? It's 1 over x times x plus h. That's it. Nice. Okay, let's do one last one here. Okay, let's see what we can do with this one here. Okay, for f of x equals square root of x, find the difference quotient. Find the difference quotient. Okay, so f of x equals radical x. So what's the difference quotient? F of x plus h minus f of x all over h. This is going to equal radical x plus h minus radical x all over h. Now, what I'm going to do next is a little sneaky. Okay, I'm going to do a little sneakiness. You probably wouldn't know to do this intuitively, but I'm going to use something called the difference of two squares to simplify. So I'm going to say that, this is x plus h plus radical x over radical x plus h plus radical x. Now, why am I doing that? Because if I have this pattern, a minus b times a plus b, that's a squared minus b squared. It's called the difference of two squares. And you can prove that to yourself just by multiplying it out. I'm going to get a squared minus or plus ab minus ab minus b squared. Okay, and the middle terms cancel out. So if I call this a and this b, and this a and this b, what's going to happen is I'm going to end up squaring these things. It's going to be the difference of two squares. So this is going to be equal to the square root of x plus h squared minus the square root of x squared, which is really nice because it's going to allow me to get rid of the square roots. And this is going to be x or h times the square root of x plus h plus the square root of x. Okay, so now the squareds and the square roots cancel out, and I'm just left with x plus h minus x all over h times the square root of x plus h plus the square root of x. And lo and behold, again, the x's on the top cancel out, and the h on the top cancels out, leaving me with just 1 on the top. This is like 1 over 1, right? 1 on the top. Okay, and so this is going to be equal to 1 over the square root of x plus h plus the square root of x. Oh, okay. So when we had f of x equal radical x, we had this thing. Okay, the difference quotient was that. Okay, so let's add that to our list. Let's go back up here. Okay, add that to our list. Oh, we didn't do this.
Professor, I have a question.
Yeah.
So the only reason you multiplied by the positive square root x plus h plus
Right.
is to get rid of the
squareds.
The square roots.
The square roots on the top. Yeah. These are called the conjugates. These are called conjugates. When you have a plus b times a minus b, those are called conjugate pairs. Okay, and I multiply, this guy here by its conjugate so that I can get a squared minus b squared. So I can get them squared.
Can you do it vice versa?
Can I do it? Yeah, you could. If this was a positive, you could do a minus minus.
Got it. Thank you.
Sure. Who is that, Jess?
Yeah.
Okay. This was minus, right? Yeah, that was minus. This is plus. Okay. So yeah, let's add that to our list. Okay. So our list here is that we've got, what was it? The square root of x. The function was the square root of x, and this was 1 over square root of x plus h minus the square root of x. Okay, so we're going to take these guys and we're going to borrow them for a second. Okay, I wonder if I could borrow it. Let's see if I could borrow this. What could I do here with this guy? Can I copy and paste him? Can I do a control C on that and just borrow him? Can you be borrowed, sir? I could really use your help on the next section here. Okay, so let's look at 1.4 and let's look at what is called differentiation. 1.4, differentiation. Okay, let's see if I can do like a control V here. Oh, nice, yes, perfect. Sweet, he can be borrowed. Awesome, awesome sauce. Okay, so let's look at our curve again, right? Let's look at our x squared curve. Okay, I'm just going to look at the curve. Okay, in the first quadrant, positive curve. Okay. So I'm going to call this x. I'm going to call this x plus h, and I'm going to call this the secant line. Okay, you good with that? Okay, so I'm gonna go to Desmos now, and I'm gonna set this up in Desmos. Okay, just so that it's a little cleaner in what I want to show you. Okay, so hopefully you can see my Desmos here. So let's do the x squared curve here. I don't know if this is gonna give me the desired result I want, but that's okay. Okay, so let's just look at 1 to 2. Okay, again, I want something a little bit curvier. I don't know, it's just fine, I guess. I go from 1 to 2. Okay, let's see what we got here. What was the secant line from at 1? This is 1, 1, right? So this is 1, 1. So I'm gonna draw the equation of the secant line here. For 2, that's 2, 4. So 1, 1, 2, 4. Okay. So
X plus h.
this is going to be y equals, the slope is going to be up 3 over 1. So the slope is 3. X. Okay. And then the y-intercept, I want to move down. I think 1. Nope. I want to move down 3. Nope. 2. Yeah, move down 2. So now you can see that the red here is the secant line. And I could say I just only want these values from 1 to 2. We'll say we only want them from 1 to 2. 1 to 2. Okay. So let's use our braces here and go 1 is less than x, which is less than 2. Okay, did everybody see that that's the secant line now? Okay, and I could even put the dots here. Okay. I'm going to label 1, 1, and I'm going to label 2, 4. Okay. Let's label those points. Okay, does that make sense? That I have the curve in black and I have the secant line, right? Okay, so now what I'm going to do is I'm going to do something a little sneaky here. Okay, I'm going to try to bring this point 2, 4 closer and closer and closer to 1, 1. And I want to see what happens. Okay, as the difference between x and x plus h goes to 0, Okay, as the difference between these 2 points go, what happens to the secant line? I want to see what happens to the secant line. So let's see. So I'm going to be a little sneaky here about this. And I'm going to say that this line is based on the points. So I'm going to actually use something called point slope form of the line. And I'm going to say, yeah, as this point goes to 1, 1, I'm no longer going to, I'm going to turn this off, okay? And I'm going to say that the first point, right? So y minus 1, okay, is equal to, so I'm going to use point slope form, m, and what's m? M is 3 in this case. Actually, it's not. And we'll get to that in a minute. Well, let's just do m as 3 for right now. Okay, m. Okay. 3, and then this is going to be x minus 1. Boom, there we go. There's that line, right? There's that line. Okay, cool. So same line, same points of intersection, right? But I'm just making a line now, okay? But I want to see what's going to happen if I bring this point closer and closer. What's going to happen to the secant line, this secant line? Okay, so I want to try to animate this as best as I can. So what I'm going to do is I'm going to change the 3 here based on the point. Okay, based on this point here. I'm going to call this point A, comma, point B. Okay, AB. Okay, I'm going to add a slider for A, and I'm going to add a slider for B. Okay, right now they're both at 1, so they're at 1, 1. Okay, the line is going to be the slope. So the slope of the line is going to be y2, which is B. Okay, y2, which is B, B minus 1, y1, over x2, which is A, x2, which is A, minus 1. Okay, that's going to be the slope of my line. Okay, and so right now there's no line because the points, okay, I want to be on this. What do I want to do here? Let me think about this for 1 second. So they got to be x squared. Oh, okay, I get this. This has got to be this. This has got to be a squared, because if I plug in x, it's got y has to be squared, right? So this has to be a squared. Sorry about that. A squared. There we go. Okay, and so this has to be a squared. Okay, minus a1. There we go. Okay, and so we can get rid of the b then. Okay, and we can see that, okay, as a increases, okay, maybe I'll zoom out a little. Okay, as a increases, okay, as a decreases, we'll say, as a gets closer and closer to 1, we see that the secant line gets closer and closer to the curve. Okay, and that when it's really close, let's let A be 1.000001. Look at that. Boom. This no longer becomes what we call a secant line. Look at that. Oh, that's so nice. Okay. It no longer becomes something called a secant line. It becomes a tangent line. Okay. So let me show you that again. Okay. As I go up, right, we've got this secant line, but as the point comes down and gets closer and closer and closer to 1, it starts becoming a tangent line. Okay, it's tangential to the curve. And so again, if I get really close, like 1.00001, it actually becomes that tangent line there. Maybe I'll make the tangent line a different color so that it's really easy to see. Okay, so that tangent line, boom, right? That's the tangent line to that curve. And then again, we can see that, okay, as the point gets closer and closer to 1, okay, at 1, there is no line because it's undefined. The slope is undefined. But if I just get close enough, I could even get really close on the other side, 0.999999999. Okay, and so you can see that that's the tangent line. That's the tangent line. I'm going to go to projector mode because I don't like this. This is okay. So does everybody see that the secant line becomes the tangent line when I approach 1? Does that make sense? The secant line here becomes the tangent line. Does that make sense? Hopefully that makes sense.
Yes.
Okay. So when something gets really, really, really close to something, what do we call that? When we approach a value really, really close, yeah, Oscar says it's a limit. Exactly,
limit.
that's a limit.
Oh.
So what we're going to do is we're going to take the limit of this. Okay. Okay, so we're going to take the limit of this as h goes to 0. Oh, okay. So we want the limit of f of x plus h minus f of x all over h as h goes to 0, and that's going to give me the tangent line, not the secant line. Okay, that's going to give me what's called the tangent line. And that tangent line also has another description. It's called the instantaneous. I can't spell today. Instantaneous rate of change. Okay, it's the instantaneous rate of change. Okay, the tangent line. Okay, instantaneous rate of change. Okay, so let's look at f of x equals x squared. Okay, let's look at example 1 here. F of x equals x squared. What is the limit as h goes to 0 of f of x plus h minus f of x all over h? Well, we already know what the difference quotient is. We just did that, right? Isn't that 2x plus h? So isn't this the limit as h goes to 0? That's this guy here, right? 2x plus h, isn't that the difference quotient? Yeah, we already did all that work.
Mm-hmm.
Yes. Yeah.
Okay. So this guy is the limit as h goes to 0 of 2x plus h. So what if I plug in 0 for h, what's left over? 2x. And what we call this limit of the difference function, okay, the difference quotient, the limit of the difference quotient, we call that the derivative. Okay, so we say this is f prime of x is equal to this. So we say that f prime of x is equal to 2x. And we say that is the derivative of f of x. Okay, that's the derivative of f of x. Okay, so let's do it for the other ones here. Let's say that f of x is equal to 1 over x. What's the derivative? What's f prime of x? Oh, that's f of x plus h. It's the limit, sorry. This is the limit as h goes to 0 of f of x plus h minus f of x all over h. So the limit as h goes to 0, again, we already calculated that for 1 over x. What was that? That was 1 over x times x plus h. It was, oh, I'm sorry, there's a negative there. It should be a negative. Okay, and so what is this guy? This is going to be negative 1 over x times x plus h. But now let's plug in 0, right? Let's plug in 0 for what? H. So this becomes negative 1 over x times x plus 0, which is negative 1 over x times x, which is negative 1 over x squared. So that's the derivative. So f prime of x is equal to negative 1 over x squared. That's the derivative for that one. Oh, okay. This is not number 1, by the way. This is number 2. Okay, let's do it for the next one, number 3. Let's do it for the next one. Okay, so if we have f of x equals radical x, we want to find the derivative of that. Well, f prime of x is equal to what? Okay, so for this one, we're going to say that the limit as h goes to 0 of f of x plus h minus f of x all over h. Again, we already calculated this difference quotient. That we did in the previous section. This one was what? This one was 1 over radical x plus h. 1 over radical x plus h plus radical x, right? So now let's plug the h in for 0, and we get 1 over radical x plus radical x. So this is 1 over 2 radical x. Oh, okay. So the derivative here is 1 over 2 radical x. And again, what does this tell me? It tells me that if I have this function, then the derivative, okay, or the slope of the tangent line at any point here, the slope of the tangent line at any point, okay, is equal to this function. Okay, it can be defined by that function. Okay, so let's see how this would work. Let's do number 4 here. Find f prime of 2 if let's do 1. F prime of 1 if f of x equals x squared. Okay, so what was f prime of x? Well, wasn't that 2x? So what's f prime of 1? That's 2 times 1, which is 2. And what does this tell me? This tells me the slope of the tangent line when x equals 1. Oh, okay. So the slope of the tangent line when x equals 1. Okay, so let's look at our parabola here, right? This was x squared. So let's look at our parabola here. And it tells me that when I'm at 1, 1 on my parabola, what's the slope of the line? What's the slope of the tangent line? Well, it's 2. The slope of the tangent line is 2. F prime of 1 is equal to 2. That's the slope of the line there. The slope is 2. Okay. Okay, let's see what else we got to cover today. Okay. Ooh, this is a good one. This is spicy. Let's do a spicy one. Okay, let's spice it up. What number are we on? We're on number 5. Okay, here's a spicy one. Okay, for f of x equals x cubed, find f prime of 1 Let's do f prime of negative 1. Okay. Dang. Okay, let's see what we get here. Okay, so what do we want? We want the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay. So now this is going to be equal to the limit of f of x plus h. What's f of x plus h? Well, f of x plus h is just my original function, but instead of x, I have x plus h. So this is going to be x plus h cubed minus, this is as h goes to 0, as that difference goes to 0, right? Remember that it was x and then it was x plus h, and we want this thing to go to 0. When we want h, the difference between those 2 points, to go to 0. Where's my arrow here? It's approaching that. Okay, minus x cubed, that's what f of x is. F of x is x cubed all over h. Okay. Let's bring this over here. So the limit, I've got to cube this out. The limit as h goes to 0 of x plus h times x plus h times x plus h. Okay, minus x cubed all over h. Now if I multiply this thing out, this is gonna, let's FOIL this out first. That's gonna be x squared plus 2xh plus h squared. Okay. And then I'm gonna have to multiply that by x plus h again. So this becomes x squared, or sorry, x cubed, and then this is gonna be plus x squared h plus 2x 2x squared h, okay, plus 2xh squared, okay, let's do the last one here, plus xh squared plus h cubed, okay. Okay, multiply all that out. This I can combine some like terms here. This is combine the first two and the second two here. This is going to be plus 3x squared h plus 3xh squared plus h cubed. Okay, now I'm going to take this guy, I'm going to pull him over here. I want the limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Okay, so we want to find the derivative of this thing. This is f prime of x, right? Find the derivative of this cubic function. Okay, so the x cubes cancel. That's kind of nice. X cubes there cancel. Okay, and so we're left with 3x squared h plus 3xh squared plus h cubed all over h. So this is the limit as h goes to 0. I'm going to factor out an h. Okay, all over h. These h's are going to cancel. And now what I'm going to do is I'm going to say the limit as h goes to 0, okay, of 3x squared plus 3xh plus h squared. Now, the only thing that survives here is the first term. Why is that? Because if I plug in 0 here and I plug in 0 here, those go to 0. Those go to 0, and I'm just left with 3x squared, which it's not determined by h. Okay, so that's 3x squared. So the derivative is 3x squared. That's the derivative. Okay, and so the last thing we want to do is say, well, what's the derivative evaluated at 1? Well, that's just 3 times negative 1 squared, which is equal to, okay, which is equal to 3, right? That equals 3. Now, what does this look like? Okay, what does this look like? Well, I'm glad you asked, because we're going to go to Desmos and see, well, what the heck does all this mean? Okay, what does this look like? So let's try to model this. Okay. Okay. So what this looks like is this. Let's put in x cubed this time. Let's get rid of these guys here. Let's put in x cubed. Okay. And then put in a cubed here. Okay, and we have this guy here, right? So it's saying that at -1, the slope is what? At -1, -1 here, the slope is 3, right? The slope is 3. Okay, so let's see if that's true. Let's see if that's true. I'm going to get rid of this guy too. Okay, let's see if that's true. The y equals mx plus b, right? mx plus b. That's the equation of a line, right? Okay. So what did they say that the slope was, though? The slope of the tangent line at -1. The slope, we calculated that slope. We calculated the slope to be 3. So I'm gonna say, oh, that's 3. And then I'm just gonna say, okay, well, where would this be located if it was tangent? Oh, look at that, it'd be right there. Look at that. Isn't that the tangent line at -1? So what's the tangent line? Well, the tangent line is y equals 3x plus 2. 3x plus 2. Boom. Yeah, there you go. Okay, that's the tangent line. Okay, and 3 is called the instantaneous rate of change. It's the instantaneous rate of change. We'll talk about instantaneous rate of change a little bit later. Okay, but what we really want to just know is that is the slope of the tangent. Oh, thank you. I was fighting a sinus infection like a week ago, and it was not good. Okay, because I get very grouchy when I get sick, and it's not fun. I'm not a fun person to be around when I'm sick. So it's like everything annoys me. But I'm getting better, which is good. Discuss B. Okay, B is the y-intercept, right? B is the y-intercept. So I just know that the y-intercept here has to be 2, because that will go through the point -1, -1. The line that has slope 3 that goes through point -1, -1 has a y-intercept of 2. See that there? Has a y-intercept of 2. Okay, and I could calculate that out using the point slope form if I really wanted to. Okay, maybe I'll do that. I could show you that this is actually the okay, this is actually the equation of the tangent line is the line that goes through -1, -1, right? Because what is y equals x cubed, right? Well, what is, if I plug in -1, well, y is equal to -1 cubed. Well, what's -1 times -1 times -1? Isn't that -1? So when x is -1, isn't y -1 on this curve, right? This is called the x cubed curve. It's called a serpentine because it looks like a snake. Okay, but here at -1, we're at -1. So that's -1, -1. Okay, makes sense? Okay, so right here we're at -1, -1. We want to know what's the slope of the tangent line, or what is the equation of that tangent line, right? So we could use point slope form. Y minus y1 equals m times x minus x1, right? What the point that it went through, we knew that it goes through that point, but then we used the derivative to calculate the slope. of the tangent line. So the slope of the tangent line was 3. M is equal to 3. And so this is y minus -1 is equal to 3 times x minus -1. Okay. So this becomes y plus 1 equals distribute 3x. This is going to be a plus 1. So 3 times 1 is 3. And then we subtract 1. And we get y equals 3x plus 2, which is exactly the equation of the line that we had in Desmos, right? So this is going to go through a y-intercept of 2. Does that help, Oscar? Okay, cool. Awesome. Good question. Good question. Okay, let's see what else we got going on here. Okay, so let's write this down. The derivative okay, of f of x called f prime of x is referred to as the slope of the tangent line. Okay, at a specific point on the original function f of x. Okay, so again, if we have a curve, say we have a curve, and we have the derivative is the slope of the tangent line. Okay. So here we have x, here we have our y value f of x. Okay, so here's the point x f of x. And the derivative is the slope. So m is equal to f prime of x. The derivative is the slope of the tangent line. Okay. What number are we on? Are we on 5, 6? I can't remember. We're on 6. Okay. Okay, let's do a couple more and we'll call it a day. Okay, number 6 here. Okay. For f of x equals 1 over x, find the equation of the tangent line at x equals 2. Okay, so let's find the equation of the tangent line. So what do we need to find the equation of the tangent line? We need a point and we need the slope. So how are we going to find the slope? Well, we're going to find the slope by getting the derivative. What was the derivative of 1 over x? Anybody remember?
Negative 1 over x squared.
Yeah, thank you, Dominic. Yeah, negative 1 over x squared. Remember, those are the ones. There are a few that you need to memorize in this class, and you got to memorize, right? What is x squared? Well, that's 2x. What is 1 over x? That's negative 1 over x squared. And what is radical x? That's 1 over 2 radical x. So, you know, if this is f of x, then this is f prime of x. So just make sure that you have those memorized. Okay, so, okay. We also have another one that we could add to this. You don't need to have this memorized, but we just derived this one. Oops. What was x cubed? And remember what we got found for x cubed?
3x squared.
Yeah, very good. 3x squared. Okay. So, yeah, very cool. Okay, so the derivative is this. The derivative where though? Where are we looking? If we looked at this equation, it looks like this, right? Okay, it looks like my hyperbola goes like this. Okay, that's f of x equals 1 over x. That's what that looks like. Okay, but what do we want? We want at 2, right? We want at x equals 2. So this is 1, this is 2. At x equals 2, we want the equation of the tangent line at x equals 2. Okay, so at x equals 2, what do we need? We need the point. Well, what's the point? Well, it's 2, 1/2. How did I get that? How did I know that that was at 2, 1/2? Because what's the original function? Isn't the original function 1 over x? Right? So if x is 2, then what's f of it? F of 2? Isn't that 1 over 2? What's f prime of 2? Isn't that negative 1 over 4? Does that make sense? So what's the slope of this line? What's the slope of this tangent line? What's m at 2? What's the slope? The slope is f prime of 2, which is negative 1/4. That's the slope of the tangent line. Okay. So now let's use point slope form to get the equation of the line in slope intercept form. So we have y minus, we don't really have to put it in slope intercept form if we don't want to, but we can. Okay, so what's the point that we're working with? The point is 2, 1/2. What's the slope that we're working with? Negative 1/4. We found that from the derivative. So this is y minus y1, that's 1/2, okay, is equal to m, that's negative 1/4, times x minus 2. x1 is 2, right? Okay, so let's distribute. This is negative 1/4 x. What's 2 times 1/4? That's 1/2. Well, that's kind of cool. Okay, so y minus 1/2 is equal to this. Let's add 1/2. What's 1/2 plus 1/2?
One.
Yeah, 1. Thank you. Thank you. Yeah, it's 1. Okay, so what's the equation of this line? The equation of this line is y equals negative 1/4 x plus 1. Okay. So let's see if this makes sense. Let's see if we did it right. Let's check it. Let's check our work. Okay, let's check it. Check the work. How are we going to check the work? We're going to plug this function and this equation into Desmos and see if it is a tangent line. Let's do that. Okay. Let's do that. Okay, so what was the function? The function was y equals 1 over x, right? Pi equals 1 over x. Okay, 1 over x. Okay, and then yeah, and then what's the other equation that we want? The other equation that we want is what our equation of our tangent line at 2, right? At 2. I mean, I could put the point, what's the point that we wanted to use? We want to use point 2, 1/2, right? So 2, 1/2. Okay, so 2, 1/2 is there, right? So we want the tangent line through this point. Does that make sense? Through that point. So what was the tangent line? It was y equals negative 1/4, negative 1/4, okay, x plus what? Plus 1. Whoa, look at that. That's so cool. That's the tangent line to that curve. That's amazing. That's calculicious. Yeah. I created that word. I'm going to coin it. It's going to be in the Webster's dictionary. Calculicious. That's the feeling you get when you get a calculus problem right. It's calculicious. Okay. Okay, so very, very nice. Very nice. I like what I've done there. That's good. Okay. What else we got? Yeah, let's talk real quickly about discontinuous. Sound. Can you hear me now? Sounds good. Saying the only thing that stands between me and a 4-day weekend, this class, yeah, you guys, okay, yeah. So let's do this last thing and let's get the heck out of here, okay? Exactly. Rock and roll. Okay, functions are discontinuous functions that are.
Professor, you're not sharing the screen.
Oh, thank you. Share the screen. Boom. Sharing is caring, right? Sharing is caring. So make sure that we're sharing the screen there. Okay, functions that are discontinuous have a break in the gap or have functions that are discontinuous have a break in the graph or have sharp corners are not differentiable at these points. Okay. For example, if I have something that looks like this, okay, then f prime of 0 does not exist. There is no derivative at when x is 0. Okay, it just doesn't exist. Okay, why? Because there's no limit. The limit there goes to infinity at 0. So there's no derivative. Therefore, so there's no limit. Therefore, there's no derivative. If you can't have a limit, you can't have a derivative. Okay, what about this one? Why is this one not differentiable at 0? Why is this one? It's continuous, but it has this sharp corner. Why are sharp corners not allowed? Well, remember, what's the definition of derivative? The definition of derivative, definition of derivative, okay, the definition of derivative is that the limit as h goes to 0 of f of x plus f of x plus h minus f of x all over h. Okay, that's the definition of derivative. That's f prime of x. Okay, so what do I need? I need a limit as h goes to 0, right? I need a limit. But, here's the big but. Okay, but, pun intended. Okay, but how can I have a limit, right, from the right be something? So what's the slope? What's the slope of this curve on the right side? Well, the slope here is 1. And then what's the slope of the curve on the left side? The slope is -1. And at this point here, we can't determine whether or not that slope, right, whether or not this slope, m, is -1 or +1. We can't determine that, right? So we say that f prime of 0, again, does not exist. Now, does f prime of 1 exist? Yeah, it's 1. That's the slope at 1. What's the slope at 1? 1. But it doesn't exist. Okay. Okay, some other graphs where it does not exist look like this. If we have a graph that looks like this, okay, then at A, f prime of A does not exist. Okay. Prime of A does not exist. What's another one where at A? Well, if we have like a piecewise function that looks like this, sharp corner, right? Sharp corner. Sharp corner, no derivative. Okay, so again, f prime of A does not exist. Okay, what's another one? Again, this one's kind of interesting. Why does that have no derivative at A? Because the slope of the tangent line is undefined. F prime of A is undefined. Therefore, f prime of A does not exist. Okay. Okay, that's it. That's it for today. I'll see you guys back here on Tuesday. Okay.
Thank you, Professor.
Have a good weekend, Professor.
Thank you.
See you later, Professor.
Bye.
Bye.